In this video, we're going to talk about the impact the variability of ion concentrations have on action potentials. I'm Matt Halter. This is Bio 5, Cabrillo College, Corona Summer 2020. What we're really going to be talking about in this video is mainly the variability of potassium, but we have to use the same principles if we are introduced to variability of other ions, such as calcium or sodium. So let's take a look at this. Now, if we look at the normal action potential graph, or at least a portion of it, we generally have a resting state of negative 70 millivolts and threshold at negative 55 millivolts. That is to say, for an action potential Downing neuron at the axon hillock, that first voltage gated sodium channel will only open or be activated if the neuron reaches threshold at the axon hillock, which is negative 55 millivolts. This slide is showing our normal chemical gradient of potassium, a higher concentration of potassium inside the cell, and a lower concentration of potassium outside the cell. Certainly I should have charge in here, but I'm not overly concerned with charge right now, especially with potassium, which does not have an electrical gradient favoring it to leave the cell. So the variability will be as follows. Hyperkalemia represents elevated potassium levels in the extracellular fluid, but more specifically, an elevated concentration of potassium in the extracellular fluid. And it's really important that we understand that we're talking about concentration. So there could be an increased concentration of potassium in the extracellular fluid due to loss of water, or theoretically it could be to gaining more potassium ion, which means the chemical gradient for potassium has decreased. There's less incentive for potassium to leave. Certainly potassium is still going to leave the cell because there's still a higher concentration of potassium inside the cell than outside the cell, but the concentration is not as big, not as steep, so it's not going to leave as quickly and as readily as normal. So that means the cell is going to retain more potassium than normal. If the cell retains more potassium than normal, it's retaining more cations in the cell, which is going to make the cell interior more positive at its resting state. So if we look at the slide that represents this, we see our normal resting state at negative 70, we see threshold. But if it's more positive in the cell, this purple line is now representing the new resting membrane potential for potassium. That is during hyperkalemia. And if we have increased the resting membrane potential here, I don't have a number value for this, but let's just say it's negative 60 millivolts. That means it only needs to move 5 millivolts to get up to threshold, where normally going from negative 70 to negative 55 is 15 millivolts. So we're closer to threshold, and the neuron can be excited with a smaller graded potential. We don't need as great a stimulus during hyperkalemia because the resting state of that cell is closer to threshold. Now let's take a look at hypokalemia, as the term suggests, is a diminished potassium concentration in the extracellular fluid. That's what I'm trying to show with this really small potassium right here. If hypokalemia exists, there is a steeper gradient, more incentive for potassium to leave the cell down its chemical gradient. More potassium leaves the cell, more positive charge leaves the cell. It's going to make the cell interior more negative. So what's that going to do to the resting state if the cell interior is more negative? Well, if you guessed it's going to be further from threshold, you're exactly right. Because during hypokalemia, it makes the cell more negative. So let's just say this purple line here represents negative 80. And that's 10 millivolts further away from threshold. So instead of having to move the normal 15 millivolts, to get up to threshold. Now 25 millivolts of voltage change is required to get up to threshold. So this applies to all sorts of ions in the body. It can apply, like I said at the outset, sodium, calcium, chloride. So one thing we need to think about is what kind of conditions are going to cause changes in ion concentrations in the body. And I'll suggest it has more to do with probably with changes in fluid content or water volume in our body rather than changes in those particular ions. And I'm not saying it cannot be changes in those ions, but the concentration is definitely impacted by the volume of water that changes throughout time, say if we're super dehydrated or overhydrated.